Hi, my name is Kevin Emery. I am a software engineer and a quantum computer enthusiast, and I decided to start a YouTube video on quantum computing made easy. There's a lot of videos out there that cover theory and math, and we're going to cover a little bit of that, but what I want to focus on is step by step, how do you actually run a quantum computer programmer with minimal fuss? Let's get right to it. So we're going to start in Google, close all these other tabs. And we're going to look for, not China humanoid robots, no. IBM Quantum, and Qiskit is the language we're going to use, Qiskit documentation. So we do that Google search, and the top link here is going to say IBM Quantum documentation. Let's hit it. And we see here there's an API reference tab. If we go there and hit Qiskit SDK and look at Python, and select Python. Then the link I want to follow is this top link. It says Quantum Circuit Model, Qiskit.circuit. This is a nice page for beginning quantum computers. It's got an example of some very simple quantum computer code and a diagram that we expect it to draw of a circuit. But how do we run it? Well, instead of talking about configuring a whole Python installation on your machine, which has its own can of worms, we're going to use Google Colab. So we'll go to Google and we'll just do a search for Google Colab. The very top link is going to say welcome to Colab. And if you're signed in, you should be able to get to this page that says Open Notebook. If you get to this page, then you can also hit the New Notebook right here. And also, for later, it's going to be important. Notice this is a Jupyter notebook, Jupyter. We'll just keep that in mind for later. For now, we're just going to hit New Notebook here or here. And it should get you easily enough on a page like this where it says Start Coding or Generate with AI. If you're having trouble, try making a new Gmail address first so that you have a Google sign-in and sign in with your Google account, and then go to Google Colab, make a new notebook. We're going to copy the code from the IBM Qiskit documentation into our new Google Colab Jupyter notebook. Just copy and paste. All right. Now, theoretically, if we run this, it should draw this picture for us. And it'll show us the structure of this basic quantum circuit. Immediately, of course, we run into an error. It couldn't be that easy. We have module not found error. All right, fine. No module named Qiskit. And if we read this carefully, we say it says you can manually install dependencies using pip or apt. So the exclamation point before the pip install command that we're going to use says that it's an environment command and not actually a Python command. And the command we need is just exclamation point pip install Qiskit, just like this. At the very top of the script that we copied in, let's hit play again. Downloading Qiskit. So we're making progress. It's actually downloading this Qiskit, Qiskit, and we have another error. That's another missing optional library error, and kindly enough, it points an arrow at the line of code that it's having trouble with, which is this very last line of code in the script we copied where it says circ.draw. Circ is our variable for the circuit, so it's trying to draw the circuit. And it says a little further down, you can install it with pip install pylatex enc. Okay, so just so I don't make a spelling error, I'm going to copy the name of this pylatex enc, and we'll add its installation at the top of the script, right under where we installed Qiskit, pylatex enc, and hit play again. All right, now it's downloading pylatex enc. We're making good progress. And it says another missing optional library error. What's it this time? Pylatex enc is required. You can install a pip install pylatex enc. We just did that. Okay, so it's throwing an error saying we need to do what we just did. So it's Google time. missing high latex ENC library, even though it is already installed. What have you to say about this, Google? AI overview. We're not using AI exclusively to generate our code, but we are going to make use of Google AI in order to troubleshoot issues and maybe also gather some snippets of code throughout this video series. Okay, it could be incorrect Python environment, virtual environments, kernel restart, Jupyter Colab. Look at that, Jupyter Colab. If you are working in a Jupyter Notebook or Google Colab environment, changes to the environment, like installing new packages, may not be recognized. Solution, restart the kernel. Have you tried turning it off and back on again? Go figure. Okay, so in order to turn it off and back on again, essentially we go to Runtime, Restart Session right here. When I click Restart Session, are you sure you want to restart the runtime? Yes. Okay, it doesn't really look like it did a whole lot, but we're going to try running it again now that we've done a restart. And there we have it. So building a quantum circuit really is that simple. All you have to do is find some quantum code, copy it into Google Colab, and run it, and then troubleshoot the errors with Google AI. But understanding what this circuit does, that's of course where the meat and bones is. You can find a lot of information on that online, but I do want to discuss it very briefly. So looking at the code that we copied in order to draw this circuit, we see this expression. This UV looking character with a slash through it is called psi. It's a lowercase Greek letter psi. And they use psi to represent, it's like a placeholder for the quantum state, the entire quantum state. This pipe and then the shallow up and down sort of greater than looking symbol collectively is called a ket. And so we have a psi inside of a ket. We read this as ket psi. And what it means is the quantum state is equal to. So ket psi, or the overall quantum state, is equal to this. We have a fraction. In the numerator we have this. In the denominator we have this. So you add them, in order to get the probability, you add the number of kets in the numerator together and then divide it by the square of the denominator. The reasons for this are mathematical, and it has to do with trigonometry and the way that they represent the state of a quantum bit on something called the Bloch sphere. If we do Google search for what are the axes on the Bloch sphere labeled in quantum computing, it's a great search to go to images, and you can see lots of different pictures of the Bloch sphere. One of my favorites is this one right here. So you see there's three axes. There's the x-axis here, the y-axis here between I and minus I, and the z-axis here between 0 and 1. And you see how it draws the quantum state as a point on the surface of the sphere, and you see these triangles. Now, if you're familiar with trigonometry, you'll remember that right triangles use square roots a lot to calculate the hypotenuse. So for example, if you have a length of 1 and a length of 1 on the two legs of the triangle, the shorter sides, then the hypotenuse is the square root of 2. So that has a lot to do with why it is that we have a square root of 2 in the mathematical representation. But basically this equation means that it has a 50-50 probability because it's 1 over square root of 2, and we square that to make 1 over 2. A 50-50 probability of it being ket 0, 0, 0 or ket 1, 1, 1. So it's a superposition where all three of the quantum bits in our circuit are the same, and they're either all zeros or they're all ones. There can't be any mix of zeros and ones. And as we see in the comments for our code, that's called a GHZ state. We passed 3 into the quantum as the argument for the quantum circuit. Here where it says circuit equals quantum circuit 3, because we have 3 qubits. As we can see in our diagram, Q0 is a control, and then we have it acting as a control with 2 controlled NOT gates, controlled CX or controlled X or controlled NOT. And what a controlled NOT gate does is it flips the value between 0 and 1 if and only if the control bit Q0 is 1. But because we passed our Q0 through a Hadamard gate, that creates a rotation on the block sphere that puts it into a 50-50 superposition between 0 and 1. And when you use that as a control bit, it has the effect of entangling the target bit, Q1, with the control bit, such that they can either both be 1 or they can both be 0. And then we do that for Q2, another bit, and now all three are entangled, such that they can all be 1 or they can all be 0. Let's modify the program very slightly, just so that we can have a sense of freedom with it and make it our own instead of a copy-pasted. And we'll delete the 3 and put a 2. That now we're defining a quantum circuit with only 2 qubits. And as such, we don't have a qubit with index 2 to pass into the second controlled NOT gate, so we're going to delete these 2 lines of code that represent this right here, the Q2. And we'll just put our 2 qubit circuit through a single controlled NOT gate, which is just going to draw this part of the diagram here. And we'll hit play again, now that we've modified our code. There you have it. So there's a lot of fun you can have playing around with this, and we'll cover some more advanced things like histogram plots, as well as some other gates besides just the Hadamard gate and the controlled NOT gate in future videos. I hope you enjoyed listening and watching. Please hit like and subscribe and all that fancy jazz. See you next time.